Hey, this is Animashi Moroda from Group DRP, and I'm going to be taking you through the first part of our machine learning assignment. These are the contents of our presentations. This is the flow of how they are going to be presented. So our main problem we are solving is poverty in Uganda, and we're going to be using the trade patterns of Uganda to determine how poverty correlates with them and how we can solve poverty in Uganda. So first, let's get the context of Uganda. In Uganda, our population is approximately 45 million, and then our economy is a mixed one, where agriculture was mostly dominating, but now we are diversifying into other services and industries. Then our main trade partners are the East African Community, the UAE, China, and India. Then our currency is Ugandan shillings, but it's majorly unstable against the USD. So why trade matters is because it contributes approximately 41.5% of Uganda's GDP, according to World Data Bank statistics. And then these are the related works. We see that the export-led growth theory supports trade in that it states that if you increase your exports, then you're going to increase your trade. Then we have the energy dependency influencing economic stability, and the time series model is widely used in macroeconomic analysis. And then that machine learning is increasingly applied in economic forecasting. And then that the research gap is the limited integrated exploratory data analysis on Uganda's long span trade data. Then our problem statement is that whereas Uganda is actively participating in trade with other countries, we don't know which trade sectors are actually improving the poverty status in Uganda and which ones are increasing the inequality gap. So that's why our machine learning will come in and show us how that comes in and how it solves our problem of poverty. Then we see that poverty is conducted only a few times in Uganda, a few years, while trade is conducted every year in Uganda. So we have some missing values of years poverty wasn't conducted, and then every year trade is surveyed. Yeah. So we divided our problem into two categories. We have the domain application problem and the computational problem. We have these points under the domain application problem, including fluctuating exports over decades. We have instability in annual export growth rates. We have trade shocks impacting economic stability. And then in the computational problems, we have high dimensional data sets. We have long time series because our data sets are going to span from 1960 to 2024, those are 64 years. And then we have some missing values in early years because we see that poverty wasn't surveyed in some years, while trade has been surveyed each and every year. So we also have extracting insights from multivariable data. So that's also part of our computational problem. So our objectives on this are that we are going to pre-process and clean the 64-year multivariate trade data set. And then we are going to identify significant structure breakpoints. We are going to model correlations and features. We are going to evaluate the extracted insights. And so the contributions are going to be a clean analysis-ready data set, 7 to 10 statistically significant breakpoints, and then a feature importance ranking, and then validation metrics showing machine learning EDA that reveals 30% more patterns than conventional methods. Yes, so I will hand over to my other colleague to continue with the other presentation. Thank you so much.
Hello everyone, my name is Aroho Prisla and I will be taking us through dataset description and exploratory data analysis. So our dataset is a comprehensive containing indicators for GDP, poverty, trade, exports, imports, and energy use for Uganda from 1960 to 2024. These are sourced from the World Data Bank and the Uganda Bureau of Statistics as per 2024. So the first challenge that we met while doing our EDA was missing data values from the earlier years. Using careful imputation strategies, we normalized the features to ensure fair comparison, detected outliers that would have made our models wrong. So this step of preprocessing is so critical to ensure the quality of our analysis. We also moved to the output results for our normalized data. These are the visualizations. After we normalized our data, you will notice that there is a trend of sudden increase from earlier years to current years. There has been an increase in the trends of GDP, of exports, and the energy use over years. We will also move to the unsupervised learning. In unsupervised learning, we were able to cluster different years with similar trait characteristics. For example, there is a cluster that will show a period of high export growth and a cluster that will show a period of high import dependency, which helped us group these within different historical regimes. Then we also moved to semi-supervised learning that we also used. Here, we refined our understanding of feature interactions. Graphs show energy inputs. They also show commodity prices and how they correlate with different GDP and poverty and energy regimes. So we successfully identified key breakpoints, hidden patterns that seem simple with every learning point. Like here, regime prediction, we used the random forest and improvement over baseline labeled only. After semi-supervised 0.909, the improvement will show us a negative 9.1%. The method comparison, self-training, good for high confidence pseudo labeling. Label propagation, best for graph structured relationships. Co-training, effective with multiple feature views. Active learning, most efficient labeling strategy. Then we also did some anomaly detection, and the best individual model gave us 0.909. We had a deployment ensemble of self-training models for anomaly detection, implemented active learning for efficient data labeling in future years, and we also leveraged co-training when new indicator types became available. Thank you.
Hello everyone, I'll be taking you through the model selection and deployment. So now if we have to look at the models, we have the label spreading, a sample of self-training models, active learning, co-training. All these are semi-supervised models of learning. So under the label spreading, the targeted application, here we look at the economic regime classification. And under the technical and scientific justification, we say it performs best for regime prediction due to the natural graph structure. Then for the ensemble of self-training models, the targeted application is anomaly detection, and the technical and scientific justification, it provides more robust results by combining multiple model perspectives. Then the active learning model, the application which is targeted is the feature data labeling. The technical and scientific justification, it achieves comparable accuracy with 75% less labeled data. Then for the co-training model, we have the multi-view analysis under the targeted application. Then under the technical and scientific justification, it effectively utilizes different feature views to improve the learning process. Then next we have the conclusions and limitations. So the conclusions, we have that machine learning-based EDA successfully revealed hidden patterns traditional methods missed. Then the energy policy and export diversification they are critical for Uganda's future in trade. Then for the limitations, we have the missing data, the flag imputed values and visualizations. Then the sample size, it assembles the methods. Then the data source inconsistencies, priority rules, outliers, robust scaling, structure breaks, regime-specific models. Then the next steps, we have the regional scope. This will extend the comparisons to trade partners. Then the causal analysis, machine learning-based grandeur, causality tests. Then the sectorial analysis for each economic sector in Uganda individually. Then recommendations, we invest in renewable resources, diversify the economy. We can replicate the data set to cover mostly the ESC, East African community. Then we can develop more case studies for research from this data set. And the references we used the World Data Bank and the UBOS 2024 Statistical Abstract 2024. Thank you for listening.